How to deal with clearances in a tolerance chain. Clearances are typically present in most CAD assemblies and can be tricky to handle. An example here in this toy gun. The interface between the two frame parts. A bit of clearance is present between the extruded boss and the hole. Let's break it down to a simple example to show a systematic approach for how to deal with clearances. How do we set up the chain if the boxes are spaced with a little bit of clearance? Let's create a new calculation sheet for the example. We go to the 3D model and align in normal view to take a nice screenshot for our tolerance chain illustration. We paste the screenshot and the coordinate system to the canvas and fit the content to the canvas. As in the first episode of the series, we are interested in the gap between the blue part and the cradle. We mark that by blue arrows, indicating the point of interest. We go ahead and add help lines to mark our elements for the tolerance analysis. Note that we ignore the clearance between the parts and mark the help lines on the functional surfaces of the parts. Next step is to add parameter arrows, A, B, C, D. We start on the left side of the point of interest and follow through all the way to complete the chain to the right side of the point of interest. The trick is to ignore the clearance spaces. We go ahead and add data to each parameter row, matching the row with the part, and adding the nominal value of the parameter together with the tolerance. We need to do this for all parameters. Then clicking Save. We check the positive direction and automatic derive the transfer function by clicking the FX button. We get a worst-case estimate for the point of interest. We can change the evaluation method to Monte Carlo by a single click. This approach is equivalent to an assembly where the parts are pushed to the extreme position. In this case, all the parts are pushed to the left. Note that this has no impact at all compared to the case with clearance. The results are the same. This method applies to pinhole fits as well. In pinhole fits, you would expect a tangent contact. The approach is simple. You simply ignore the clearance when setting up the stack and imagine that you put the fit to its extreme location. If we examine a little bit more advanced case with multiple pinhole connections, and let's say that we are interested in the overlap of the two arms, it is the exact same approach. The nominal overlap of the arms may be a lot smaller than first anticipated and can be illustrated like this by pushing the parts to their extreme positions. Care to diameter values or radii are needed in order to get this right. We can illustrate the point of interest like this. Let's go ahead and add center lines. We also need help lines at all the interfaces. It is easiest to start from the center and out, and increasing the length of the help lines, line by line. It will help us when adding the parameter arrows. Next step is to add parameter arrows. Let's start from the right side of the point of interest. The first parameter is the distance from the tip of the yellow part to the center. We designate this one with the label A. Next up, the inner diameter of the yellow part. Note the alternating direction of the arrow. We start from where the last parameter arrow ended. We continue the alternating approach until we reach the center. From here, the chain transition from one center axis to the other. We designate this measure F. We continue the alternating approach, adding arrow G and H. We complete the tolerance chain by arrow I, from center to the tip of the blue part, reaching the left side of the point of interest. The illustration is now complete. Now we need to add values for our dimensions and their respective tolerances. Note that in this example, diameter values and not radii are entered. We will compensate for this in the next step. We define the positive direction by clicking the arrow in the bottom right corner. This should result in a negative value for the overlap. Let's save the entered values and get some help to derive the transfer function by clicking the FX button. The automatic transfer function setup ensures the right plus-minus accounting. But before jumping to conclusions, we need to edit the transfer function to use radius values instead of the inter-diameter values. We do this by editing the transfer function and multiply all diameter values by 0.5. Click Enter to save and recalculate the results. Note that the result changes from +1 to -2. It is important to get this right. We can add an upper specification limit of -1, equivalent to a requirement that there should always be minimum 1 mm overlap in the point of interest. Note that by the worst-case evaluation method, this calculation fails. We can change the evaluation method to Monte Carlo simulation and simulate 1,000,000 samples in no time. The calculation now passes, as the probability for that all the parameters fall into the worst-case scenario at the same time is very low. So dealing with clearances can be tricky and can impact performance of critical functions. To achieve the most robust solution, you can model interfaces with no clearance using local compliant mechanisms. In example, the interface between the yellow and gray part here. Often interfaces are modeled with even clearances. Seen here in the section cut, clearances are present on both left and right side. A more robust solution would be to have a defined positioning surface and some flexible features acting as nesting forces to always position on dedicated positioning features without any play. A detailed section cut is shown here. The feature on the right side is more flexible with lower stiffness, thinner and taller, to ensure it acts as a local compliant mechanism pushing the yellow part towards the left positioning feature. Here's an example for a pinhole interface with high demands, high volume production, high rotation speed, and high number of cycles. The triangular shape together with cutouts ensures a slight overlap to always ensure that there are no clearance in the fit. Flexibility can be clever built into parts in clever ways, also in sheet metal or other processes. In other cases, regular springs or custom springs can be used. Alternative methods are wedge-like shapes, set screws, or if you are working with injection molded parts, crush ribs can be a solution. When using crush ribs, you work in the plastic deformation area of the material so that it yields during assembly and adapts to the interface. If you have watched our case of the Norbauer Seneca keyboard, you know that Norbauer and Company is striving to make the world's best mechanical keyboard. This translates into no rattle and clear position of all parts. One of the tricks is to cleverly eliminate clearances in pin joints. In the section cut, you see that a compliant nesting feature is positioning the stabilizer axle to solid positioning features, eliminating all clearances in the fit and making it robust to variation. In case the parts are off the mean value, no problem. The design absorbs the variation and ensures optimal performance. Always.
Do you know the quality of your designs? We do.